As three great adventurers once said, "You have my sword, and you have my bow, and my axis." It's a Z-axis. Anyway, if you're looking to add a new dimension to your game dev skills, this video is for you. Perhaps you've just made your first game in Godot, you've put in some sprites and a few nodes, or maybe you're an experienced developer who's just never worked in 3D before. Either way, taking the first steps away from the familiarity of sprites and pixel art can feel pretty daunting. But I'm here to tell you that it doesn't have to be, and that Godot actually makes this transition pretty smooth. First, the good news. Godot is built in such a way that most of the concepts you learn when making a 2D game directly apply to 3D. This is especially true for the functionality part of your game. Many of the nodes that you might have used so far actually have a direct 3D version that works in pretty much the same way. So instead of using node 2D, we simply use node 3D instead. The same is true for area, collision shape, static body, character body, camera, raycast, audio stream player, and so on. Most of the properties on these nodes are pretty similar, and other nodes like timer and animation player don't even have a 3D equivalent. They just work the exact same way as in 2D. And this actually applies to programming as well. Detecting if a raycast 3D is hitting something is done using the isColliding function, just like in 2D. And as usual, you can move a node 3D by modifying the position. Of course, positions now have a third component that can be modified, the Z-axis, but otherwise the procedure is the same. And then, the bad news. The bad news is that while Godot tries its best to ease this transition, the world of 3D graphics is vast and complicated. While 2D games work by drawing sprites, in other words flat images onto the screen, 3D games combine a lot of different asset data, such as meshes, textures, character rigs, and animations, with the in-engine rendering tools such as shaders, lighting, particle simulations, and post-processing effects. The pipeline for this can quickly become pretty complicated, and it's definitely an area where I see a lot of misunderstandings. But fear not. This video should clear up a lot of the confusion and teach you how you can approach this with as much complexity as you'd like. Creating aesthetically pleasing 3D scenes doesn't have to be rocket science, and we can often rely on the ease of use of Godot to help us out. I've split this video up into two sections. First, we'll look at functionality, how we can design and prototype 3D games in Godot. Then, we'll dive into graphics. We'll get a good overview of the many terms thrown around when working with 3D assets, we'll nerd out on workflows and how to best use these assets in Godot. And finally, we'll learn how to render them beautifully in the engine. This video is meant to serve as an overview, not a follow along, so lean back, grab your favorite snack, and let's figure this out. But first, this video is sponsored by Zenva. If you want to know more about Godot, make sure to check out Zenva Academy. They offer great beginner and intermediate courses, including a free introductory course on Godot. Zenva combines fun and practical learning through professional video tutorials, written lessons, and interactive quizzes. And what's really cool is that you'll build real projects across various genres from RPGs to bullet hells. Zenva also has a wide range of courses on Python, Unity, Unreal, and other essential tools. With a single subscription, which includes a 7-day free trial, you unlock over 300 courses. Use the coupon code below to get an extra 20% off the first year of your Zenva subscription, on top of any existing site-wide discounts. The offer is valid for the first 50 subscribers, so make sure to use your coupon today to start your game dev adventure. So we're in Godot, and we want to go to the top here and switch from 2D to 3D. And that's pretty much it for this video, so if you enjoy— Alright, there's maybe a bit more to it than that. Let's create a 3D scene, name it main, and save it. We can create something to look at by going plus or hit Ctrl A to add a new node. We'll search for mesh instance and add the mesh instance 3D. And here Godot supplies us with some primitive meshes that we can use. I'm going to choose a new box mesh. And we can of course orbit this box by holding down middle mouse, pan using shift middle mouse, and zoom using scroll. Just like in 2D, selecting something and hitting F will focus the view on that node. And by holding down the right mouse button and using the vast keys, we can move in free look mode, which is a very nice way to move around, especially when designing levels. And adding shift to this will make you fly faster. In 2D in Godot, we normally work with pixels. Moving a node 1 unit corresponds to moving it 1 pixel on the screen. However, in 3D, this is not the case. Instead, it is common practice to equate 1 unit to 1 metric meter. And many assets that you find online will be scaled to fit this. As we can see, this box here is currently 1 meter on all sides. And if we look at the transform, we can see that all of the position data is in meters. And we can of course adjust this here, or we can use the gizmos just like in 2D. We can switch between select, move, rotate, and scale, or use Q, W, E, and R. Here we can move the node on different axes using the arrows, rotate using the arcs, and scale using the squares. To scale uniformly, simply click and drag outside the gizmos. Holding down Ctrl while translating toggles snapping. And pressing this box here, or T on the keyboard, will switch to local mode. In local mode, the gizmos follow the orientation of the node, and in global mode, they are simply ignored. A quick tip is that you can actually bind these manipulations to happen on a key press similar to a program like Blender. To do this, you go to Editor, Editor Settings, Shortcuts, and if we search for Begin, we can bind keys to rotate, scale, and translate or move. So I've bound rotate to Shift R, and now if I press that, I can rotate freely, or bind it to an axis, say the X-axis, by just hitting X, and we can now rotate around the X-axis. Clicking will apply the rotation, or right-clicking will snap it right back. Very cool. Now, before we spend hours upon hours making large and beautiful 3D environments, it's probably a good idea to start with a prototype. And a very common way to do this is by using a technique called Greyboxing, also known as a level blockout. Here you use simple shapes to lay out a rough draft of your level. This way you can make sure the level works well before getting bogged down in the details. And this is one of the things that Godot makes very easy with its built-in CSG nodes. CSG stands for Constructive Solid Geometry and allows you to quickly make levels and props by combining simple shapes. And in the end, you can even export your Greybox scene and bring it into a 3D modeling program such as Blender to use as a base. So let's try it out. When prototyping, I almost always work with snapping enabled. So at the top here, we can enable snapping or press Y, and we can configure the snap under Transform, Configure Snap. I'll set this to 0.1, 10 degrees, and 10% scale. Now we can add a new node and search for CSG, and as you can see, there are different ones in here. I'm going to start with a box, and here we can simply click and drag on the handlebars to scale it. If I hold down Alt, it's going to mirror on both sides. And a nice thing about this is that we don't need to add collision separately. We simply go to the right here and enable Use Collision, and now we can collide with it. So let me just make a quick wall here. And let's say we wanted to add a window to this wall. Well, in this case, we can use subtractive editing. So under this CSG box, I'll add a new CSG, and this time let's make it a cylinder. I'll position this where I want the window, and I'll make sure that it sticks out on both sides of the wall. Then to subtract this from our box, we simply change the operation from union to subtraction. And as you can see, we have a round window. And we can very easily adjust this to do all kinds of things. Say we wanted this to be kind of an archway instead. I would simply drag this down and scale it. And we have an archway. We can also increase the sides on the cylinder to make it look a bit nicer. Very cool. And you can do a lot more with CSG in Godot, but this is enough to get started. So let me put together a quick prototype using these techniques. Oftentimes when making levels, I will go to the top right here and click on the axes to change to that view. Just a really nice way to view everything from the side or the top. And to exit, I just click and drag with middle mouse. Now sometimes I will use a CSG combiner node, so let's hit plus, CSG combiner, and this will combine all child CSGs into one. So for static geometry like these rooms, for example, I can take pretty much everything and put it under this one CSG combiner. Just remember to check Use Collision on that node since everything is now one. And so I've blocked out these two rooms, and I've intentionally left them pretty blank. At this point, I'm starting to get ideas for how this scene might look in my head, but for the Greybox, I've concentrated on just getting a rough layout. I also know that I'm going to be using tileable assets for the walls, so I've stuck to simple 90-degree angles. Feel free to get as crazy with this part as you'd like, or exclude it completely. Not all projects need a Greybox. Now I should mention that so far this is turning into an architectural level, but sometimes you want to work with more organic environments, such as for large outdoor scenes. Here it is common to use a terrain tool that allows you to sculpt and paint a terrain to suit your needs. Godot doesn't have a built-in solution for this, but there is an extension called Terrain 3D, which is quickly becoming the go-to tool for terrain in Godot. Creating terrain is a really fun and creative process, but it's not within the scope of this video. Let me know if you'd like to learn more about terrain and foliage in the future. Alright, so to play our game, we need to add a camera. So let's add a new node, camera, and select camera 3D. I'm gonna move it over so that it can see our level and rotate it down. Remember, we can always preview it by selecting this toggle. Cool, so the camera now has a view of our level. And if we now click to play or press F5, it will ask us to set a main scene. We'll hit select current. And our level looks not very exciting, even for Greybox. That's because by default, Godot uses a preview sun and environment in the scene view, but not when running the game. In fact, we can toggle the preview sun and environment using these buttons here. And if we expand, we can even adjust settings such as the sun's direction. And we can also add them to our game. So let's simply hit add sun to scene and also add environment to scene. As you can see, this creates two new nodes, a directional light, which is our sun, and a world environment. The sun we can now rotate to adjust where it's shining from. And the world environment we'll talk about later. And now if we play, we can see our level. But what fun is it if we can't move around it? And for this, we need some kind of character controller. But just like in 2D, creating a solid controller can actually get pretty complicated. And the needs of the controller entirely depends on the game that you're making. Is it first person or third person? Does the camera move freely or is it bound to a character? Do you need jumping, double jumps, wall jumps, stairs, slope, sprint, crouch, prone, swim, attack while swimming? It's too much. And this is not a video about character controllers. Luckily, there are a lot of good resources about making different types of controllers available. So instead of spending the next hour programming a controller that might not be right for you anyway, I'll link to some that you can check out. I would recommend starting simple. You can always expand on your controller as the game progresses and you get more comfortable. I've also gone ahead and created a very simple character controller to use for prototyping first-person games. I call it the Proto Controller. You can download it for free. It's under the CC0 license, so you can use it for anything. It's designed to be simple and has basic movement with options for jumping, sprinting, and a free fly mode that I find super useful when testing. To import, simply take the Proto Controller folder and drag it into your add-ons folder in Godot. If you don't have an add-ons folder, you can simply go ahead and create a new folder, name it add-ons, and now we can drag our Proto Controller in there. And that's it. We can now go here, take the Proto Controller scene, and drag it into our Greybox level. We can get rid of the camera we created before. And now when we play, we can look around, move using the arrow keys, and even jump using space. To get control of our mouse back, we hit escape. And if we go into the controller, we can see that it's super simple. Again, this is intended for easy prototyping, so I've kept it very bare bones. It has a character controller to drive movement, a mesh instance for temporary graphics, a collision shape, and under the head node is a camera 3D. The script references the collider and head nodes, so leave them be unless you want to modify the script. Which, if you want to, is as simple as clicking the script button, and here is all of the code. On the top node, we can choose which features we want to include, as well as adjust some speeds. I'll enable sprint and free fly. We just need to make sure that we also go under input actions and bind the appropriate keys. And this is exactly the same as 2D, so to add input, we go project, project settings, input map, and here we can add actions for all the things we want to do. I'll add some for the movement as well so that I can bind them to my own keys. And now that I have the actions, I can bind keys to them. And to put this into our controller, we just take these names and put them into our input actions. And now if I play, I can move using the right keys, I can even sprint, and I can toggle into free fly mode, and of course toggle right back. Awesome! Now we can make levels and start testing them, so we're almost done with functionality. But I quickly want to touch on physics. 3D physics works much the same as 2D, and uses many of the same nodes. To create a static collider, we use a static body 3D node with a collision shape 3D as a child. Here we add a shape resource, size it to fit, and that's it. For physics simulated objects, we use rigid body 3D, again with collision shape. A quick thing to note is that Godot can be a little sensitive when it comes to scaling colliders. Scaling uniformly should be fine, but non-uniform scaling will generate a warning and probably lead to collision weirdness. Just a heads up. Now, one thing that I really recommend you do in most cases is to switch to the Jolt physics engine. Jolt is currently being implemented into the engine and is planned to replace the default Godot physics. It has many advantages, mainly in terms of better performance and more stable physics simulation. For me, it has fixed much of the weird behavior that I sometimes run into with the default physics. It's also much better at scaling. Still, there are a few differences, so if you're unsure if Jolt is right for you, I'll have a link to where you can learn more and follow its progress. If you're using Godot 4.4 or later, Jolt is already part of the engine and just needs to be enabled by going Project, Project Settings, scrolling down to Physics, 3D, and setting the Physics engine to Jolt Physics. It'll ask us to restart, and Jolt is now enabled. On previous versions, I'm building this in Godot 4.3, we first have to install it as an add-on. So we'll go to the asset library, we'll go online, search for Godot Jolt, we'll click and download, hit install, save and restart. And now we can enable it in the same place under Project Settings, 3D Physics. We have to check Advanced though, and under Physics Engine, we have Jolt Physics. And again, we'll have to restart. And as you can see, we didn't have to change anything about our game. We can run it and move around just as before, but now all the physics nodes will use Jolt instead. So that's how we can start prototyping and building functionality for our 3D game. Because there's more to 3D than just making the game really ridiculously good looking. But that's fun too, and graphics is probably the biggest difference between 2D and 3D development. So welcome to Giraffix Park. When working with 3D graphics in Godot, I think most of the work fall under three main pillars that all contribute to the look of our game. I like to call them the 3Ds of 3D graphics. First we have the assets, the models with textures and materials that we place in our scene, the lighting, the lights that we set in our scene, and the environment, the rendering choices we make that affect our scene. If the look of a game isn't working, it's probably because one or more of these pillars or Ds isn't doing what it should. You could of course argue that shaders and VFX need their own pillars, but for the sake of keeping the scope of this video just somewhat reasonable, we'll skip those topics entirely. Plus, the 5Ds of 3D graphics just sound silly. So let's begin by having a look at importing and setting up 3D assets in Godot, and then we'll move on to lighting and environment. Now this is where I see a lot of people get confused, and that's understandable. When it comes to 3D assets, there's often a lot of terminology being thrown around. If you're a 3D artist, you need to know what kinds of assets and formats Godot expects so you can best tailor your workflow to fit. But even if you're not a 3D artist, it's important to have a solid understanding of what these terms mean, so you can implement assets created by others correctly in the engine. So just to make sure that we're all on the same page, here's a 1-minute overview of all the things that make up a common 3D game asset. If you have experience creating 3D assets already, feel free to skip ahead exactly 1 minute. The shape of our model is called the mesh. It's the actual geometry or polygons that make up the object. We can easily assign a color to a mesh, but if we want to texture it by painting with multiple colors, we need to make a UV map. A UV map is a 2D representation of our mesh. Each point on the map refers to a point on the mesh. This is called unwrapping, and you can think of it like peeling an orange and then laying the peel out flat. Texturing is most commonly done by painting directly onto the mesh. The 3D program then uses the UV map to apply this to the texture. The result is a 2D image that can be overlaid onto the model. Next, we create materials to simulate the surface properties. Is our model rough like wood or smooth and shiny like metal? These properties might vary over the surface, so we create textures for them as well. Now, some assets, such as characters, need to bend and animate. This is done using a rig that defines the movable bones. Each bone is mapped to a specific part of the mesh so that when it moves, the mesh comes with it, which looks funny when it's done wrong. Finally, a game asset can have animation data, such as animations that move the bones of the character. Hopefully that gave you an idea of what makes up a common 3D game asset. Now let's look at how to get your game assets playing nice with Godot. Officially, Godot supports these model formats, with GLTF being the recommended. GLTF is an open standard that is rapidly increasing in popularity, and personally, I've had the best results with it. If I'm working with a model in another format, I will most often re-export to GLTF using Blender. It has solved many issues for me. GLTF comes in two versions, .gltf and .glb. GLB is the binary version. It's smaller and recommended for most cases. Godot also supports .blend files, which means if you're working in Blender, you can save your Blender file directly into your Godot project and it will import correctly. Behind the scenes, Godot is actually calling Blender to export to GLTF, which means that you have to have Blender installed for .blend files to work. Now, for this part, I'll be using some assets from the amazing K-Kit and Kenny. I've made a few tweaks and bundled together just the ones that I use if you want to try some of these things out on the exact same assets. Or if you want the full packs, definitely check out the original creators. Links for both in the description. So here I have a chest with some coins in it. the chest is made up of a GLTF file containing the model and a separate PNG texture. So let's create a models folder in Godot, select it, and drag in our chest. From here, we can drag it into our scene, and voila, a chest. The texture isn't applied, but we'll fix that in a second. Now, a very important thing to note here is that next to the model is this scene icon. Often, a 3D asset will contain more than a single mesh. It might have an entire hierarchy of objects. To make this easy for us to manage, Godot treats a GLTF file like a Godot scene. And we can go ahead and open it like any other scene. It's going to tell us that this scene belongs to our GLTF file, so we can't modify it. That should be done with your modeling program. But we can open it and see what's in here by pressing open anyway. And here we can see all of the nodes that now make up this asset in Godot. Even if you import a GLTF file with just a single mesh in it, Godot will put it under a root node and create a scene for it. Now, sometimes our assets might import without issue, but oftentimes we need to make adjustments. So let's select the GLTF and go to our import window. Here are a bunch of settings, most of which you can ignore for now. But one you might need right away is root scale. This allows us to adjust the scale of the imported model. So in this case, I think 1 is fine. While we can adjust many things in the import window, a lot of the really important import settings are actually under advanced. We can click the advanced button or simply double-click the file, and this will open up the advanced import settings. Don't be scared by the fact that it's called advanced. This window simply gives you much more control over the different parts of your model. Here we can see the nodes making up the scene, and if we select one, we can set import settings for just that node. Say we didn't want to import the chest lid, well then we could simply hit skip import for just that node. And if we select the scene at the top, we get the standard import settings. We can also go under materials to see all of the materials that got imported. And the cool thing is that we can override any of the imported materials with our own. So let's create a material for this chest. I'll right-click, create new, resource, and I'll search for standard material. Here's the standard material 3D. I'll name it matte chest. And now in the advanced import settings, we can select the default material, go under use external and enable that, and point to the material that we just created. Which means that if we re-import, we can now go to our material, and any changes we make here will apply to our chest. And to add our texture, we simply drag it into the albedo texture slot. And this is probably a good time to talk a bit about the standard material. The standard material is a very powerful and also flexible PBR material that can be used for anything from wood to metals, vegetation, and emissive surfaces. It can even act as a simple toon shader by changing the diffuse and specular modes to toon. The standard material really deserves an entire video in its own right, because it has so many properties that you can adjust to get the look you're going for. And of course, we can use textures or maps to set these as well. But to get started, here's a quick overview of the most common ones. Albedo, the base color of your material. If you use an albedo texture to set this, it can use both the RG and B channels to define color. You can also use the alpha channel to define transparency if you mark the material as transparent. Metallic, how reflective is the surface? This is a value that goes from 0 to 1, where 1 is completely reflective. However, internally, even at 0, the material reflects a tiny bit, just like in real life. A metallic map requires only one channel. Note that once in a while you might run into something called a specular map. This is an alternative to the metallic workflow that Godot uses and is not supported. Roughness. How smooth or rough is the surface? A material with a low roughness value results in sharp reflections. As the roughness increases, the light becomes more scattered and the reflections start to get fuzzy. A roughness map also only requires one channel. Some assets provide a smoothness map instead. This is the same as roughness but inverted. In this case, I would recommend inverting it in an image editor before importing to Godot. Normal. Here you can add a normal map to simulate depth. It changes the way light interacts with the surface to display smaller shape details. However, the mesh is not actually affected by a normal map. Because of this, the effectiveness will vary depending on the viewing angle. A normal map uses the RGB channels. Be aware that Godot uses normal maps in OpenGL style. Some normal maps that are created for DirectX will appear inverted. If your normal map doesn't look right, you can go to the import window and select Normal Map Invert Y. This will convert it from one style to the other. Ambient Occlusion. Here you can add an AO map that affects how much ambient light reaches the surface. In other words, it can darken the parts of your model where light has a hard time reaching, and it uses one channel. Emission. Does the surface emit light? We can set this manually or use an emission map. But this is more pertaining to lighting, so we'll move on. There are of course many other types of maps like height or refraction, but these are for more advanced use cases, so we won't go into them here. At this point you might be thinking, that's a lot of textures for just one model. And many games will definitely only need a fraction of them. But if your game needs them all, it can be a challenge to fit that many textures into the game. Because of this, it is common to use an ORM texture and material. Remember that ambient occlusion, roughness, and metallic textures only require one channel each. This means that in practice they can be combined into an ORM texture, where each map occupies either the red, green, or blue channel. Godot fully supports this workflow with a version of the standard material called ORM Material 3D, which can be combined with regular standard materials without issue. And on the subject of materials, for some workflows, the 3D artist will set up all the material properties in the 3D software. In this case, the textures will often be packaged with the model file. This is called packed or embedded textures. Here, for example, I have a barrel, which just consists of a DLTF. The material and texture has already been set up in Blender and packed into the file. So if I import it, Godot will extract the textures and place them next to the DLTF. And the model is ready to use. We can always go under the import settings and at the bottom under embedded image handling, choose what happens to the textures. As you can see, this is set to extract by default, and so it appears next to the model. And if we want to, we can also extract materials. So if we double click the barrel, go under actions, there's an option here to extract materials. So I'm just going to extract them in the same place. And now we can configure the material. This is useful because not all materials in your 3D program will transfer perfectly into Godot materials, in which case you might want to adjust them here. Alright, so our test is imported and looking great, but how do we actually start using it in our game? Now if we play the game, I can run right through it, so we'd at least want to add some kind of collision. And what I see a lot of people do is go here to Open Scene and choose New Inherited. This creates an inherited scene based on the GLTF file. What this means is that we can add new nodes to the scene and even override some properties, but we can't modify the original hierarchy, which turns yellow to indicate this. So we could add a node here, we can add a script, make some changes, and when we're satisfied, save it as a new scene that we can use in our game. And this works, but there are a few problems. First of all, using inherited scenes quickly gets very confusing. What's part of the original asset and what's not? Also, it breaks very easily. If I make a change to the asset and it gets re-imported, it can be hard to predict what happens to the inherited scene, and your changes might get removed. And doing it this way means that we are basing our game functionality on a graphics asset. This is generally a no-go, especially in more complicated scenarios. In fact, most of the time we're doing the exact opposite. We build functionality without fancy visuals, and then bring in those visuals as we'd like. So instead of using this to create an inherited scene, I recommend that you use nesting. With the nested approach, we create a new scene that we have full control over. So I'll make it a 3D scene, name it chest, and here we drag in our model. This allows us to freely create and configure gameplay nodes and then import or swap out our graphics as we see fit. Then when we are happy with it, we can save it and start using it in our game. This approach is also much more stable because any changes to the GLTF file won't affect our game logic. It will just update this one nested scene. Of course, it might happen that you need to reference something inside the nested scene. I would generally advise you to be careful when doing this because, again, things become more likely to break. But if we need to, we can expose the child nodes of the scene by enabling editable children. If you find yourself doing this a lot, perhaps it would make more sense to split the asset into multiple GLTF files instead. Say for this chest here, if I needed to access the lid to open it, I could export the lid as a separate file. Just an option. Now there is actually a third way of structuring your scenes that I personally like for a lot of reasons. Unfortunately, it currently has a very big drawback. For this technique, we also use a separate scene, and again we drag in the model. And then we press Make Local. What this does is that it breaks the connection to the GLTF scene. This now gives us full control over the original asset, which means that we can pick and choose what we want and reorder the hierarchy. So it has some clear advantages. It's very flexible and makes it easy to separate function from visuals. But I mentioned there was a drawback. As of making this video, this is Godot 4.3, when we press Make Local, Godot will take all the mesh data in the GLTF and store it in the scene we created. That means that if we save this scene before pressing Make Local, and look at the size, it's very, very small. But if I now go in and press Make Local and save again, we can see that immediately the scene grows by a lot. Now this might be fine for very low poly models, but if the mesh is more complex, it will bloat your scenes a lot, which is not a good thing. Remember that at some point this scene needs to be loaded by your players, and if it's big and bulky, that is going to take longer. Now, improving these workflows is something that is being actively discussed in the Godot community, and I'll provide some links to where you can read more if you're interested. But for now, these are the 3 ways of implementing your model into your game, and at this moment, I would say, if in doubt, use nested scenes. So in this case, to quickly add collision to the chest and start using it, we would make a new scene. As the root node, I'll hit Other Node, and I'll search for Static Body 3D, because our chest isn't going to be moving, but we want it to be physics enabled. Let's hit Create. Let's then drag in the chest model. And as you can see, the static body expects a collision shape. So we'll hit Ctrl A, collision shape. And for the shape here, we'll choose a box shape 3D. And now we can use the gizmos to size it to fit. There we go. I'll name the root node chest, make a folder for my scenes, and save it there. And now we can start using this chest in our game. And indeed, we can collide with it. Sometimes you'll run into a model where a simple collision shape doesn't quite fit. And most of the time, I would recommend that you just go with good enough, because the simple shapes are very much more performant than the alternative. For this barrel here, in most situations, a cylinder is probably fine. But if you do need something more detailed, there are 2 things you can do. One is that you can piece together multiple collision shapes to create the shape that you want. This is probably what I do most of the time. Or you can have Godot generate a collision shape based on the mesh. To do this, we'll enable editable children on the barrel model. We'll select the mesh we want, and on the mesh at the top, we'll create a collision shape. Here we'll choose sibling, and we can choose which method to use. I'll choose single convex and hit create. Now we can move the collision shape to be under the barrel and disable editable children. I've made this barrel a rigid body to show this more clearly, so if we save it as a scene and position it over our chest, when we play the game, we can see that indeed the collisions are now pretty accurate. I'll have a link to the docs where you can learn more about when it's best to use different types of colliders. It's also not uncommon to model your own colliders in a 3D program. A good way to do that is using suffixes. But first, I'll take everything that we've learned so far and use it to replace this boring-looking Greybox with some actual assets. I'll start with these building assets. Often, low-poly models will be textured with just a few colors, and it's common for all the models to share the same texture, which is the case here. So I'll import the models and the dungeon albedo texture and create a standard material that all the models can share. Then I'll go through each of the models and point them to this external material. And now I'll create a scene and set up collision for each of them. As we talked about, this is a good example of a model that needs multiple collision shapes, so I can simply copy this one collision shape that I've created, rotate it, and move it over. And remember, whenever we duplicate a collision shape, we also have to go and right-click on the shape and click Make Unique. Otherwise, the changes that we make to the shape resource will affect both collision shapes. So Make Unique, and perfect. And now I can place them in the level. Sometimes the Greybox can get a bit in the way, so I like to lock all of the CSG nodes, simply select them and hit this lock here. And I'll do the same for all of the child nodes. I'll also disable collisions, so on the top node here, I'll remove Use Collision. And I'll assign a material that makes it a bit easier to see through it. So under Geometry, Material Override, I will create a new standard material. And on this material, I will set transparency to alpha. And for the albedo, I'll set this to a nice magenta color, as well as turn down the alpha to make it transparent. Much better. So now that the Greybox has been replaced by our custom assets, we can simply get rid of it. And now we can play our game with our assets in it. Awesome! And this is a good time to start decorating, which I'll do in the exact same way. I've already imported some prop assets and I'll set them up as nested scenes and scatter them throughout the level. So since we know how to do that already, I'll use a bit of TV magic and voila! A beautiful level. And while I'm walking through it, notice how we started with a very rough sketch, a Greybox, that allowed us to quickly move things around and prototype. And once that worked, we replaced the Greybox with some actual walls. And only once that was in place did I start decorating. Which is just a great way to make sure that you aren't spending a lot of time going into detail with something that might be scratched anyway. Now before we move on to lighting our level, so far we've only worked with hard body models. What if we wanted to add animated characters? Take for example this skeleton. It's textured, rigged and animated. And everything is packaged into the GLTF, so we can simply drag it into Godot. And if we double click it, we can see that inside is a skeleton 3D, which is the rig, a bunch of meshes, which are controlled by the skeleton. And because the file has animations, it's gone ahead and automatically created an animation player, under which we can see all the animations and set loop settings for each one individually. If I drag it into a scene and enable editable children, we can then use the animation player to play animations. But most of the time, I actually prefer to work with animations separately. So here I have a zombie character. It is also textured, rigged, and animated, but the file is split up. The first one contains just the model, texture, and rig. If we import it and double-click it, we can see that it has a skeleton 3D and a mesh, but no animation player or animations. So let's drag this into our scene. The other GLTF files don't actually include the model. They simply have the rig and animation data. As you can see, if we import one and double-click it, there's no mesh. But there are animations. This means that we can go to the import window and import this as not a scene, but an animation library. I'll hit re-import, hit OK. Then we can create our own animation player for this character. So I'll add a new animation player. And as you can see, it set the root node here to zombie. We want to make sure that that's the case so that this animation player controls the zombie. And then under animation, we go manage animations. And here we can load a library, such as the zombie idle library that we just imported. And here are the animations in that file. You can easily pack together multiple animations into one file. Say you want to have one for combat animations or whatever you like. So we'll hit OK and we can now play this animation. And if we want it to loop, we simply double-click the zombie idle and change the loop mode for the idle here to linear. And voila, you've now added the animations of this separate file to your model. This is great because you can add animations as you go, and you can even use the same animations for different characters as long as they share the same rig, which is really cool. Now you can actually do this even though the rigs aren't exactly identical. This is called retargeting and allows you to use animations on rigs they weren't originally created for, such as when using third-party animations from a library like Mixamo. I'll have a link to where you can learn more about retargeting in the description. There are also a few tips that you can use to speed up your workflow. The first one is to use name suffixes in your 3D software that Godot will then recognize when importing. For example, if I don't want Godot to import the lid of this chest, I would simply use -noimp to tell Godot not to import that node. Using -col only will convert the mesh into a collision shape and put it under a static body node. This way you can model custom colliders in your 3D software and Godot will treat them accordingly. You can also add a -loop suffix to an animation and Godot will automatically set it to loop on import. And if you find yourself repeating the same task over and over, Godot also allows you to automate the process using import scripts. These are a bit too advanced for this video, but really powerful. So I'll link to where you can read more about them, as well as naming suffixes in the description. So with some assets in our scene, we are ready for the next pillar, which is either lighting or environment. But in my experience, it's often best to work on these two things at the same time, since they affect each other. Let's start with the world environment node. Remember earlier, we took the preview sun and environment that Godot uses for viewing in the editor and added it to our scene. So we should have this world environment node. If not, you can always go to the 3 dots at the top and hit Add Environment to Scene. And the world environment node is one of the things that I really like about Godot. It puts all the common rendering properties for our scene in one place, and in combination with our lighting, allows us to really set the mood of our game. Now, probably the most important setting in the environment node is the background. This is because it not only defines what to display as a background for our scene, it also affects the ambient and reflected light that gets applied to our objects. This means that setting the background plays a huge role in lighting our scene, even if the background is never directly visible. There are many modes to choose from, but the most common are Custom Color and Sky. Custom Color allows you to choose a solid color as the background. If I'm making an indoor level and don't want outside lighting affecting the scene, I often begin by setting this to black. The Sky mode is where the magic happens. By default, Godot will procedurally generate a sky background. This means that we can go in here and adjust settings to change the look of our sky. So I can go under Sky and change the top color. I can set the horizon color, as well as change the bottom color of the ground and the horizon color of the ground. As you can see, we can get pretty funky with it. And since the sky is procedural, it will also update to show the direction of our sun. Now, in our world environment, we can also change to a physical sky. If we select New Physical Sky Material, this is also procedurally generated, but is adjusted using physically based parameters. It will produce different results than the standard procedural sky, so feel free to experiment, but know that this is slightly more expensive to render. You can also set the sky background to a panorama image, sometimes referred to as an HDRI. A good resource for freely licensed HDRIs is Polyhaven. To set up a panorama sky, we import the image. Godot supports both HDR and .exr formats. We then change the sky material to panorama sky and drag the image into the panorama slot. No matter which background you choose, we can adjust the intensity using the energy multiplier. With the background selected, it's time to start lighting our scene. But lighting is a huge topic and one of the most important parts of making a 3D game really ridiculously good looking. So I've decided to do a brief introduction to lighting here and then hopefully expand on it with a dedicated video in the future. That way we'll have ample time to dive into global illumination, reflections, emissive surfaces, and light baking. But for now, know that Godot has 3 different lights. 3 different lights? 3D lights that you can place in your scene. Directional light. This illuminates your entire scene from a certain direction. It's most commonly used as a sun or a moon. Omnilight. This emits light from a point out in a radius. It acts kind of like a standard light bulb. And Spotlight. This emits light like a flashlight, so from a point out in a cone. And all of these inherit from Light 3D, so you can adjust color, energy, and so on. A fairly common way to light a scene is to start with a directional light and then place Omni and Spotlights based on the physical lights in your scene. These can be especially great for introducing a pop of color to your game and avoiding bland areas where your directional light doesn't reach. So let me show you how to go about doing that. So let's start by adjusting our directional light. This is the main point of light in our scene, so it's the most important one to get right. I'll enable the ceiling here so we can see which shadows are being cast. And then maybe I'll just adjust the angle a tiny bit. Let me fly into the scene here so we can see it more clearly. And if we go under light, we can set the color to something a tiny bit more warm. This is very subtle, but I'll make it slightly yellow. You can also play with the intensity, but I think 1 is fine for now. I'll also go into the world environment, and under ambient light, I'll decrease the sky contribution a tiny bit. This way, less light is spilling from our sky onto our scene, which just darkens the shadows a bit, which should look better once we get inside. And talking about inside, it's time to add some light to the torches. So I'll select this one, hit Ctrl A, search for Omnilight 3D, and so it will add our Omnilight as a child of the torch. I'll move it out and up a bit. And the first thing that I'll do is definitely change the color of this to something more fire-like. So under light, I will change the color to a nice orange. Something like that. I'll also increase the energy to 2. And currently this room could really do with some shadows. So I'm going to go ahead and enable shadows on this Omnilight. This is definitely something that you want to do sparingly, since having many lights casting shadows can quickly get expensive, but I think in this case it's worth it. I'm going to make the color a tiny bit less yellow, and I'm going to go to the top here under Omni and change the range to say 15, so it really fills out the room. Now, since my torch here is set up as a scene, one of the really cool things is that we can simply add this light to the scene. So I'm going to cut it here, right-click, cut to remove and copy it. Then I'm going to go into the torch scene and paste it here instead. And now if I save this scene, all torches in our main scene are going to update automatically. And voila, we have light all over. I will also go into my world environment and enable SSAO. As you can see, SSAO, or Screen Space Ambient Occlusion, will shadow areas where light might have a hard time reaching. And that's how we can very quickly light our scene using real-time lighting. Of course, the torches here might benefit from some nice particle effects, but that's for another video. The world environment also gives us control over the look of the render. For example, we can choose which tone map to use. The tone map has a big effect on the look of our final game, but understanding what a tone mapper does is pretty technical. For now, just know that it affects the contrast curve of your scene, and unless you choose linear, it will help stop highlights from clipping. For almost all my projects, I either work in the default filmic mode or ACs. ACs is an even more contrasty curve that has become the standard for photorealism. When using ACs, I often increase the white point, and if your scene is too dark, feel free to increase the exposure a bit as well. Godot 4.4 also adds the AGX tone mapper, which is a nice alternative to the current ones. I'm glad to see progress on the subject since the current tone mappers do have their issues and the ACs look has been prevalent for a while now. I'll provide a few links to where you can learn more about tone mapping if you're interested. Finally, under Adjustments, we can apply some basic color correction, or supply a color correction lookup table or LOT for more control. A nifty trick here is to add a one-dimensional gradient, so gradient texture 1D. This allows us to control color and brightness over the range of our image. For example, if we add 2 more points in our gradient near the white and black point, we can use them to, say, bring in a bit of warmth in the highlights, make the shadows cooler, and adjust contrast more precisely by moving them back and forth. As with most color correction, small adjustments are your friend. Another thing to consider are the settings on our camera. We can go into our proto controller and adjust the camera here, but I've just placed one right here overlooking our entire scene so you can clearly see what's going on. Here we can set the projection. So if you're making an isometric game, we can change from perspective to orthogonal and adjust the size to fit. In perspective mode, we can also adjust the field of view. But to get more control over the camera, we use camera attributes. We can either set some here or go into the world environment and add camera attributes here instead. So let's set a new camera attributes practical. Here we can adjust the exposure or enable auto exposure. This is great if you have a dynamically moving camera, such as in a first-person game, and you want the camera to auto-expose based on what it's currently looking at. For example, if the player goes from broad daylight into a dark cave. This can also be seen in the scene view, so if I fly into a dark room now, I'm going to put on the ceiling. Increasing the speed allows us to see this more clearly. We can see that the camera is going to compensate when I look in shadowy areas, and if I look into the sun here, it's going to quickly expose to the right level. With scale, we adjust the exposure intensity, and with minimum and maximum sensitivity, we can limit how far we compensate for dark and bright areas. I'll disable it for now. And finally, you might want to adjust render quality. To do this, we go Project, Project Settings, and from here the settings are a bit spread out, but remember you can always search at the top. For anti-aliasing, we go Rendering, Anti-aliasing. I'll enable multi-sample anti-aliasing. For settings related to environment, we go Rendering, Environment, and enable Advanced Settings. And for lighting, we go to Light and Shadows. Feel free to play around or read more about these settings in the online docs. Alright, we made it, and hopefully before you ran out of snacks. I'm glad I could help welcome you to the world of 3D in Godot, and I hope this video gave you a nice foundation to build your 3D game on. Also, don't forget to check out Zenva Academy. Be among the first 50 people to use the coupon code below to get 20% off the first year of your Zenva subscription. Now I'm off to the grocery store for a refill. Really ridiculously good looking.